Hello everyone, hope you're doing well. So, we are going to discuss about oxidation number concept over here in this video. So, before that, I just want to discuss the previous concept. We know two things. So, I'm going to write on this side. We know about valency and we know about charge. These two things we know, right? So, valency is a whole number. So, it represents the, you can say, a whole number with no charge in it. It can be 0, 1, 2, 3, or it can be 4 also. So it's a combining capacity. It's a number of electrons an atom is going to donate, is going to share, or it's going to accept electrons. So that is valency, but we never put any charge along with the valency. Now, charge is just a simple, you can say, a very easy term we introduced in the, you can say, earlier classes. So, charge can be plus or it can be minus, right? Or it can be zero. But what is oxidation number? So, it's not valency. We never say that it is same as that of valency. And then oxidation number is like if we want to define. So, oxidation number of an atom is the actual charge of the atom if it exists as a monoatomic ion. Or we can even define, first I'll write it, then I'll explain. Or we can even say a hypothetical charge assigned to the atom in the substance according to some rules. So, what do we understand by this? Oxidation number of an atom is the actual charge of the atom if it exists as a monoatomic ion. So, let's take an example of a monoatomic ion, sulfide. We can even say Na plus. So, we say sulfur has a minus 2 charge, but the oxidation number over here is going to be minus 2 for this sulfide ion. Sodium oxidation number is going to be plus 1. So it's very important for us to write oxidation number along with the number. We need to write plus, minus, or it's 0. So it can be plus minus 0 or it can be even a fractional value. So we will see when we are going to take some examples, we are going to see it. So it's a changeable number, right? And if you go back to the chemical reactions where I taught you types of chemical reactions, in redox I told you about oxidation, right? So loss of electrons is oxidation. We know addition of oxygen is oxidation, removal of hydrogen is oxidation, loss of electrons is also oxidation, right? Then based on this oxidation number, we will introduce another way to define redox reactions later on. So we can even say oxidation number is an oxidized state. So we even say oxidation number as oxidation state also, because it's changeable. It depends upon what kind of atoms are chemically bonded to that particular, you can say, central atom. So in specifically covalent bonding, we always have a central atom and we have a side atoms. Like, let's take example of carbon tetrachloride. So in this, carbon is a central atom, whereas chlorine are the side atoms which are covalently bonded with carbon over here. So again, if you go back to the basics, carbon atomic number is 6, 2 and 4 configuration. So 4 valence electrons, 4 chlorine bonds are covalently bonded over here. So monoatomic ion or hypothetical charge, because this is not in reality, right? So it's we can't say that this is you can say in reality it exists. It is a very much hypothetical concept. But yes, we are following these rules, what we are going to discuss right now in a minute. So for assigning oxidation numbers, these are consistent with the requirement of charge balance, or you can say even conservation of charge. So they do not denote any actual charges on atom, but some kind of, you can say, formal charges which are arbitrarily assigned to the atoms to help balance the chemical equations with the help of stoichiometry and charge. So, but we need to follow these rules, because if we are not following these rules, then there is a possibility we might assign the wrong oxidation number. So again, it can create more problems. So, this concept is very much important in chemistry, specifically redox reactions, where oxidation number can change also. That we will write later on. So, let's quickly start the rules for assigning oxidation number. So, I am writing short form ON, standing oxidation number. So, the very first rule, electrons shared between two unlike atoms or different atoms are counted to be with the more electronegative atom. So now if we take an example of HCl, so I told this before that if you break this bond, so the electron pair always belong to the more electronegative atom, that is chlorine. So this is you can say between unlike atoms, the electrons, you can say, shared between two unlike atoms are counted to be with the more electronegative atom, that is chlorine. So if we have same atoms, so we will assign the oxidation number of hydrogen as +1, chlorine as -1. So hydrogen also we'll discuss in a separate point. But chlorine, most of the time, not always, but we when we write chloride, so we know chloride means Cl minus. So -1 is the oxidation number of chlorine. Hydrogen, since it's electropositive over here, it's less electronegative than chlorine, so it will acquire positive charge. Then if we have like atoms, so electrons between two like atoms are divided equally between the two atoms. So, or you can say the examples that we are talking: chlorine molecule, oxygen molecule, nitrogen molecule, so many are there, hydrogen molecule, so many. Or you can even write this statement as like this: molecules of the same element will have zero oxidation number. Simple as that. So then oxidation number of an element in uncombined state is always zero. Then we talk about the group 1 element. Group 1 is the extreme left, your left, you can say vertical column. So group 1 elements, except hydrogen, I'm not talking about hydrogen over here. Group 1 elements are called as alkali metals because most of them are going to form soluble bases. So group 1 elements: lithium, sodium, potassium, rubidium, cesium, francium. So francium I'm not considering because it's a radioactive element. Radioactivity we can discuss in a separate video, but not over here. But if we say this, all these like group 1 elements have +1 oxidation number in the combined state. They are not going to have anything else but always +1. Then if we go to group 2 elements, These are alkaline earth metals. So they have plus 2 oxidation number in the combined state. So again, exceptions can be there: beryllium, magnesium, calcium, strontium, barium. So again, last element is radium. I'm not taking that because radium and strontium both are radioactive. So we are not going to consider their, you can say, oxidation number over here. Then we talk about hydrogen. So remember this group 1 elements, they are metals, they have the tendency to donate electrons, that's why plus 1 oxidation number. And then most of the metals over here, they are group 2 alkaline earth metals, they have the tendency to donate electrons. Again, exceptions can be there. So plus 2 oxidation number will be assigned if they are in the combined state. Then we go to hydrogen. Hydrogen is going to show plus 1 and it's going to show minus 1 oxidation number. So plus 1 is with non-metals. We just took that example, HCl over here. HCl, hydrogen is plus 1 because it's bonded with the covalently bonded with the non-metal, and minus 1 with metals. So we can take example of lithium hydride. Hydrides, like most of the time, hydrides are always going to have hydrogen as minus 1 oxidation number. So lithium is plus 1 over here, hydrogen is minus 1 because it's a hydride. Name of this compound is lithium hydride. Then we go to the next rule. So now we are going to talk about oxygen. So oxygen is going to be assigned as minus 2 oxidation number, that is on a general front. Generally, most of the compounds will be having oxidation state of oxygen as minus 2. But we do have an exception, something called as peroxides. You might have heard about hydrogen peroxide. I was teaching you about that in chemical reaction and equations, where you what we were doing. Yeah, it in the presence of photolytic decomposition. So hydrogen peroxide decompose in the presence of sunlight. So it gives water and oxygen. This is a peroxide. The structure, if like you can say, the bonding we are going to see over here. So this is what we call as peroxide linkage, oxygen single bond with other oxygen. So these two are carrying minus 1 oxidation number. So oxygen in peroxide is always going to carry minus 1. So hydrogen peroxide, or wherever the term peroxide is there, but in some of the acids there is some peroxide linkage. It's not written in the name, or sometimes it's not mentioned in the name, and it's very difficult to even predict. In that case, we need to have experimental information. Only then we can find it out that there is some peroxide linkage over there. So then examples: hydrogen peroxide is there, barium peroxide is there, we have sodium peroxide Na2O2. So over here oxygen oxidation number is minus 1. Then we even have a example of superoxide. So oxygen is going to have minus half over here oxidation number. So I told in the beginning it can be fractional value also. So if you see KO2, so oxygen, if you see potassium is plus 1 because it's an alkali metal. Then if you want to see this, if we take half over here, so automatically the potassium oxidation number will, if we calculate, okay, that calculation part I haven't told you, but I'll take this example in a minute. First we'll try to understand the rules. Then oxygen can even show plus oxidation state, which is very unlikely, but in certain cases they do show. So we have an example of oxygen difluoride. So OF2 over here, oxygen is going to show plus 2 oxidation number. So now how do we calculate this? Let's try to understand it. Like, how do we calculate? We take the algebraic sum. So I had to basically explain in a rule, but let's do it. OF2, consider this oxygen as X. and you add the different you can say oxidation number of different elements, fluorine is always going to be -1. That's another rule. I'll write it. Fluorine always in the combined state is going to show -1 oxidation number, no other oxidation number it's going to show. Then molecule of the same element, if we have fluorine molecule, that's 0 oxidation number. So -1 into 2 is equal to 0. So why we are taking it as a 0? Because this entire molecule is not carrying any kind of charge, no charge. Now if we take another example, sulfate, SO4 2 minus. Sulfur you consider it as X. Oxygen is -2 on a general front. Oxygen is -2 oxidation number. So -2 into the number of atoms. If you can see oxygen, 4 atoms are there. And the whole equation will be equal to, so the whole equation will be equal to -2. Why I'm writing -2? Because you can see this is a radical. It's a polyatomic ion. So in the polyatomic ions, when you're calculating oxidation number, you have to take the whole equation equal to the collective charge which is appearing over there. So if we calculate, first we'll try to calculate. This is -2, x -2, this is equal to 0. So x will be equal to +2. That's how we ended up having +2 oxidation number for oxygen difluoride. And for sulfur sulfur S we need to calculate. Most of the time they are always going to calculate the middle element, the central atom. So x plus -8 is equal to -2. So x will be equal to -2 plus 8. So x will be equal to +6. So +6 is the oxidation state of sulfur in sulfate radical. Then we have another example, O2F2. So this you try on your own. Make sure you multiply with the number of atoms also. So this is dioxygen difluoride. So over here oxygen is having +1 oxidation number. You can try on your own. So in the similar way which I did, you can also do the same. Then this is next fluorine, -1 oxidation number in all of its compounds. Then oxidation number of halides, or you can say halogens in halides. Halides are nothing but salts of halogens. It's always going to be -1. Sulfur in sulfides, that is going to be -2, right? So oxidation number of halogens. So halogens are nothing but 17 group elements. So if from your left to right, the 17th column that you see, so fluorine, chlorine, bromine, iodine. So if they are going to make salts with the group 1 element or group 2 elements, so that's why we call them as halides, because they have the tendency to form salt with group 1 and group 2 metals. Now we are not considering the rest of the group elements, astatine and tennessine. Tennessine, we don't have much of the, you can say, literature involved. And astatine, we are not, because it has more metallic character, so we are not going to consider. So these 4 elements are famously called as halogens. Then there are many rules, but I'm not going to cover up this one rule related to coordination compounds, because first I have to explain you what is coordination compound and what coordination salts can do, and then we can have certain examples like how to assign oxidation number for them. So it's a totally different topic, so I'm not going to touch that. Then we can write algebraic sum of oxidation numbers of all atoms in a compound or ion is equal to the charge on it. So if it is not showing any charge, then you just consider it as 0, because most of the compounds are having 0 charge. So now let's take some example. We have this compound K2Cr2O7. This is called as potassium dichromate. So we need to calculate the central atom chromium oxidation number over here. So you suppose this as X. Potassium, we just did in the rule that potassium is alkali metal. So it will be always having +1 oxidation number into the number of atoms. The number of atoms are these: chromium 2, oxygen 7. Plus different elements, oxidation number will be added up. So this will be 2x. I'm supposing this chromium as X, 2x, because there are two chromium atoms. Plus oxygen is the normal oxidation, you can say generally -2. Then into 7. Now this entire equation will be equal to 0. So plus 2 plus 2x -14. So you can do, yeah, at some point of time when you are going to become more mature in redox reactions, you have to do this entire thing in your brain, that what should be the oxidation state of the central atom. So this is going to be 2x minus 12 is equal to 0. So x will be equal to plus 12 divided by 2. So this will be plus 6. So plus 6 for one chromium atom. If you multiply into 2, like for 2x, it will be plus 12. Then we go to another one, MnO4 minus. This is called as permanganate ion. So suppose it as X plus oxygen is -2 into 4. This is equal to -1. So oxygen, and generally I am taking examples only those where -1, -2 is the oxidation number. So X minus 8 is equal to -1, so X will be equal to plus 7. Writing plus and minus is very important for oxidation number. Now next example that we are going to take is calcium oxychloride. This is also one of the major component in bleaching powder mixture. So most of the time we address calcium oxychloride as bleaching powder because you have a lot of percentage of this compound in the bleaching powder. So calcium oxychloride is not a simple salt. Now in this you have OCl2. You have two ions in it. One is ClO minus. So this is called as hypochlorite ion. So in the basics where I was teaching you chemical formulas and the nomenclature part, so you can see those videos. ClO minus is hypochlorite, ClO2 minus is chlorite, then ClO3 minus is chlorate, ClO4 minus is perchlorate. So we have two chlorine over here. So one is chloride, another is hypochlorite. So we need to consider this fact, because if we don't, then our answer will be wrong, because we need to calculate. See, calcium is very pretty obvious. Calcium is +2, we know that. But we need to find the oxidation number of chlorine, and we should never make this mistake that chlorine is same over here. It's belong to different ions. One is hypochlorite ion, another is chloride ion. So for ClO minus, so if you need to calculate, so you suppose chlorine as X, so plus -2 general oxidation number of oxygen, then is equal to -1. So this will be X is equal to +1. So -2, you subtract it from +2, -1, so it will be +1. So this is +1 oxidation number, and this is for chloride it is -1 oxidation number. So this can be a very good question, that what is the oxidation number of chlorine in calcium oxychloride. So one of the chlorine atom is going to have -1 oxidation number, the other chlorine atom will be +1 oxidation number. This is how you can calculate. So in the last, I want to take this oxidation. We can define oxidation in a different way now. So this is, but in a separate video, we'll be discussing how to balance chemical reactions based on oxidation number. So increase in oxidation number from reactant to product side, that is oxidation. Then reduction is decrease in oxidation number. So we defined three concepts for oxidation for redox reactions. One is the classical concept: addition of oxygen, removal of hydrogen, etc. Or loss of electrons is oxidation, gain of electrons is reduction. That is what we call electronic concept. And then we have this last concept, oxidation number, based on this. So increase in oxidation number is oxidation, decrease is reduction. So I hope you have understood this. If you have similar examples, if you have this in your syllabus, then do practice. And I have my email ID mentioned in the description if you want to have a one-to-one session with me. Otherwise, please do like, subscribe, and share my channel. Thank you very much.